it's even thicker, and so on. What that allows me to do is put more vectors in there without it looking really, really crowded. And so the thickness corresponding to the magnitude also. Are there questions? No? Okay with it? Now, one thing I do want to mention really quick is some notation here. We're going to be doing more of these. But because we want to be able to talk about vector fields not only in 2 dimensions, but in 3 dimensions as well, we need to talk about some shortcuts to writing f of x, y. So in R2, a vector field is given or created by a function f of x, y, plus c, x, y, I, plus 2 of x, y, j. Now the interesting thing here is I can actually write this by writing it as P2 I j, and what would go in between that? A dot product, right? Exactly right. There's a little bit of notation here. Other way we might write this is I could write this as f, and this is going to come up very occasionally, of x, where x is boldface. What does it mean if I write that x boldface? It's a vector, right? With x equal to the vector, another way of writing it. Now this is both for R2, so what I'm going to do is I'm going to erase this really quick. What we're really curious about is R3. So, a vector field in R3 is generated by a function f of x, y, z. How is this going to change what I write out? To have I, j, and k, right? So if I want, I can still write it as p, x, y, z, I, plus 2, x, y, z, j, plus exactly right, r. Essentially, all this means is I'm going to have some scalar function times I, or some scalar function times j, or some scalar function times k. Now, really important here, we talk about f of x, y, z as generating a vector field. That is, for each x, y, and z, it gives us out a vector. So if f of x, y, z generates a vector field, we can say that normally px, y, z, which gives out scalars, right? I plug in an x, y, and a z value, I get out a scalar. We can sometimes say this is a scalar field. That is, when I plug in those values, I get out a point, it gives me a scalar field. Now, are we going to use that language? No, but we should probably hear it at least once. So the question becomes, if I have these vector fields in R3, how do we visualize them? So to look at an example here, we're going to look at f of x is equal to z times k. In this case, what does x correspond to? The vector, right? Because it's boldface. X gives me x, y, and z. Now, the function here, does it depend on x and y at all? No. So what do we call x and y? Function doesn't depend on them. They're free, right? They vary. They don't really matter to us. So what we want to do is we want to go ahead and visualize this. To visualize it, the first thing we're going to do is create a p-table. I'm going to choose points x, y, and z. Now I'm going to be visualizing these in 3 space, right? I'm in R3 now, 3 variables. Okay, I got to the point. Easiest point. 0, 0, that matters is z, maybe I should plug in something for z, right? Let's plug in 1 for z. Now I want you to think about this. What am I going to get out? Don't you dare tell me 1.
1K.
You need 1K, right? How would I write that using my braces? It'd be 0, 0, 1, right? What does this vector look like? Straight up, right? What I'm going to do is I'm going to come over here, I'm going to go ahead and put this point on there. I go to 0, 0, 1, from x is 0, y 0, z is 1, and it just goes straight up, right? That's good? Okay, let's plug in another point. I'm going to plug in 0, 1, 1. What's my vector going to be? Exactly the same, right? Give me half a second here. If I plot that point, x is 0, right? So I have no movement along this axis. Y is 1, so I'm going to move over to 1. And up is z equals 1. And the vector will be how long? Well, this is my vector, right? So the magnitude of it is 1. Yeah, what? Okay. I'm going to change it one more time. I'm going to put in 0, 2, 1. I'm trying to make a point. What will my vector be? 0, 0, 1. Okay, x is 0, y is 2, z is 1, and my vector is 1 unit long right there. What are all these vectors going to be?
1.
Exactly the same, right? All these vectors will be exactly the same. See, that wasn't all that interesting. Let's make it a little more interesting. Let's look at 0, 1, negative 1. Okay, 0, 0, negative 1, right? I'm going to go here. Z is negative 1, so I'm down below, right? Right here. And so where is this vector pointing? This one. Can you guess what all these ones are going to look like? That's right, right? Like that. Am I having any movement in the y or x direction?
No.
How could I obtain that from my function? I have no either phase, right? So there's not going to be any movement in the x or y direction. Which means the only thing I have to do is figure out what's happening when I vary z. That is, if I were to come up here and plug in something like 0, 0, 2, what would my vector look like then? Well, if I plug in 0, 0, 2, my vector would be 0, 0, 2, right? How long is that vector? Oh, Daddy found it?
Yeah.
Oh, it's around it, yeah. Just a second. How long is the magnitude? And it's not root 2. Well, you said root 2. It's 2 squared, and then I root it. It's how long? 2. Which means I have two options. I can either draw this 2 units long, or I can take it and make it a little bigger. And this one would be the same, right? And this one would be the same. And that one would be the same. What's going to happen down below if I go down to z equals negative 2? Same, but pointed down, right? Here's the big question, guys. As I get further away from my origin, what's happening to my vectors? The magnitude is getting longer, right? They're getting larger. That's exactly right. I still go exactly the same direction, but the magnitude is changing. If you want to visualize this, I wouldn't just have these ones, right? I would also have all of them along the x-axis as well. That is, at each point in this room, there'd be a vector facing straight out of the ground, right? Closer to the floor, they'd be smaller vectors. Higher off the ground, the vectors would be longer. Not all of them are this nice. We are not going to be graphing vector fields in 3 dimensions here that are not nice because you get all kinds of curving motion. Water flow is a really good example where we see water flow and velocity is a really good example where we can see three-dimensional vector fields. For instance, if you have a pipe coming or if you have water coming down a spillway in a dam, the water is acting in various directions with varying force and velocity. So what we can do is we can plot how the water changes, and that would be an example of a very complicated three-dimensional vector field.
How do you come up with the algebra or the secondary?
Of how water flows.
Yeah.
There's all kinds of really cool modeling, actually. All kinds of really cool modeling that goes into it. You can do it with various instruments, like you can put different things off the coast of Washington. We're trying to put in some wind turbines, and so what they've done is they've actually taken out various types of buoys. Like, they've ghetto rigged some of them in our bay, and they put them in crab traps, which is hilarious, to see how it flows down a little lower and stuff. But there are various ways to measure it. We also have theoretical models that people spend their entire careers coming up with. Like entire careers. So, yeah. Fluid dynamics. Awesome. Not my specialty though, so I won't go on about it. Okay, this being said, we know how to graph them now. We need to talk about a couple more things. There's some really specific types of vector fields that are very interesting. And one of them comes from something we looked at quite a while ago, called the gradient. You guys remember gradients? So, gradients. The gradient of a function, f of x, how do we represent it? Notation. The bell. The gradient was super interesting. It gave us all kinds of cool stuff. You guys didn't think it was really cool, but I did. How do I find the gradient? I take a bunch of partial derivatives, right? That is, when I look at this, when I look at the gradient, I take the partial, right? The gradient is the dot product of the partial derivative with I, J, K, or just I and J. So, in general, when we would define the gradient of a function f, of a vector f, or the gradient, we could say, of a function of x, y, and z, is equal to the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z, dot I, J, K, which is the same as saying partial of f with respect to xi, plus the partial of f with respect to y, j, plus the partial of f with respect to z, k. Notice this fits what we were talking about with vector fields, right? We have a function here, and what the function does is it allows us to plug in values of x, y, and z into these partial derivatives, and for each x, y, and z vector, it will give us out a vector. This type of thing, very surprisingly, is called a gradient vector field. Remember that's why. The vector field comes from the gradient. We're going to learn all kinds of cool stuff about this next time, but for now, you guys are free. You will have homework this time. I want your study guide. Do you guys want to keep your study guides? Would it be helpful for you to keep them? Yeah, you can keep them then. I just want your homework though. If you did not give it to me last time.